let me just remind everybody about the derivatives of the trigonometric functions. There are 6 of them. Derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent of x is secant squared of x, derivative of cosecant of x is negative cosecant of x times cotangent of x, derivative of secant of x is secant of x times tangent of x, and derivative of cotangent of x is negative cosecant squared of x. The reason I bring these up is because knowing all these derivatives means we know all the antiderivatives, right? We then get to say, so you could say that the antiderivative of negative sine is equal to cosine, but what we usually say instead is that the antiderivative of sine is equal to negative cosine. So if you differentiate this, the derivative of negative cosine is negative sine, just sine. And the antiderivative of cosine is sine, because the derivative of sine is cosine. And the antiderivative of secant squared is tangent of x, because the derivative of tangent of x is secant squared of x. I'm not saying the plus c, right? The plus c is there. The antiderivative of cosecant of x times cotangent of x is negative cosecant of x plus c, because the derivative of negative cosecant is negative cosecant of x times cotangent of x. So I'm going to let cat out here. Started talking too much. She clearly needs to leave. One moment. Yes, goodbye, cat. Okay. The antiderivative of secant of x times tangent of x is secant of x, because the derivative of secant is secant of x times tangent of x, and the antiderivative of cosecant squared of x is negative cotangent of x, because the derivative of cotangent of x is negative cosecant squared of x. So all of these trig antiderivatives we already know, because we know these trig derivatives. But that actually leaves a few questions. First of all, what about the antiderivative of tangent or secant or cosecant or cotangent, which we'll get to in a minute? And I know one of your teachers has already, I was looking at his lecture notes, has already gone over. I think it was Lee, not positive. But the other thing I wanted to point out was that somebody asked me this question, which I thought was worthwhile. So what if I wanted to find, let's go over here. What if I want to find the antiderivative of cosecant squared of x over 3? Or you might want to say it's the integral of cosecant squared of 1/3 x dx. There are kind of, in my mind, 2 ways to go about doing a problem like this. This, to me, qualifies as what I would call a mini U substitution, where you don't actually have to do the U substitution. So here's what I know. Here's what I'm going to say the answer is, and then we'll do the U substitution. The answer is going to be, well, if it was just cosecant squared of, say, x, the antiderivative of cosecant squared of x would be negative cotangent of x, because the derivative of cotangent is negative cosecant squared. So the integral of cosecant squared of a thing is going to be negative cotangent of that thing plus c. Now, I'm off by a little bit. I'm off by a constant multiple. If you took the derivative of this, let me ask everybody. If I took the derivative of negative cotangent of 1/3 x, what constant would you multiply by if you took the derivative of that? It's not a trick question. Yeah, exactly, 1/3. So here's the thing. If you took the derivative of this, you would multiply by 1/3, and you would get 1/3 cosecant squared of 1/3 x. We don't have a 1/3 here. So to account or adjust for that, we're going to divide by 1/3. Now, of course, I'm not going to leave it like that, because dividing by a fraction, I'd rather flip and multiply it. So this is actually equal to -3 times cotangent of 1/3 x plus c. So it is my opinion that you all are able to, or you should, what's my opinion? My opinion is that you want to take the time to be able to do these quick mini U substitutions without having to actually write out the U substitution. That doesn't mean you can't write it out. So here's how we'd actually show the work. We'd say, okay, well, if I'm trying to do an integral, an antiderivative, and I see that there's a potential candidate for U, right? There is a thing stuck inside a function. I really want to be super clear, right? This is cosecant squared of 1/3 x, right? You can't take that 1/3 x out of the cosecant squared. It's not cosecant squared times 1/3 x. It's cosecant squared of the quantity 1/3 x. So we can try a U sub where we let u equal 1/3 x. Then the derivative here, the derivative du dx is equal to, well, the derivative of 1/3 x is 1/3. And then if we isolate du, we get, I'm gonna run out of room here, du equal to 1/3 dx. And then since I don't have a 1/3 dx, I'm going to get rid of the 1/3 and multiply both sides by 3. I'm going to get 3 du equal to dx. Okay, great. So now in my integral, my dx, that's going to be my 3 du, and my 1/3 x, that's going to be u. So when I rewrite the integral here, I get the integral of cosecant squared of u times 3 du. When we anti-differentiate cosecant squared, we know the antiderivative of cosecant squared of u is negative cotangent of u times 3 plus c. And then plugging back in the fact that u is equal to 1/3 x and moving the 3 in front, we get negative 3 cotangent of 1/3 x. Sorry, yeah, that's right, 1/3 x. So I'm going to stress this every time I do it, really. If you're ever integrating something and you have just a constant multiple of x, like 1/3 times x or 5x, when you anti-differentiate that, you end up dividing by that constant. And it's because we're actually doing a u substitution, we're just not showing the work. So another example of this could be, where my ratios go? Some more excellent examples of this would be something like the integral of e to the negative 5x. You could do a u substitution. You could say, okay, I'm going to let u equal negative 5x. du dx is going to be negative 5. So du is negative 5 dx. And since I don't have a negative 5 dx, I'm going to divide this by negative 5. And I'm going to say that negative 1/5 du equals dx. So then when I rewrite this, this dx becomes my negative 1/5 du. I'm just going to go there. And e to the negative 5x, the negative 5x, that's going to be u. So this is going to become the integral of e to the u. Dx is negative 1/5. Let's pull the constant out in front. This is negative 1/5 e integral of e to the u du. The integral of e to the u is e to the u, or the antiderivative. That's going to be negative 1/5 e to the u plus c, and then plugging back in what e to the u is, we get negative 1/5 e to the negative 5x plus c. However, you could have also just said, I know that the antiderivative of e to the x is e to the x. So the antiderivative of e to the something times x, I should say the antiderivative of e to a constant times x is e to that same constant times x divided by that constant. Where you have e to the negative 5x divided by negative 5. I just wrote it as times negative 1/5. We do one more. What else do I have here? Let's do the antiderivative of, sure, let's do, let's do secant of 1/3. Nah, I did 1/3. Let's be more interesting. Let's do negative x over 2 tangent of negative x over 2 dx. Okay, so this looks like secant of x divided by negative 2 times tangent of x divided by negative 2. Or secant, you could also write it as secant of negative 1/2 times x tangent of negative 1/2 times x. Okay, here's the short answer. Short answer is, well, I know that the derivative of secant of x is secant of x times tangent of x. So the antiderivative of secant of x times tangent of x should be secant of x. The antiderivative of secant of a thing times tangent of the same thing should be secant of that thing. what do I need to divide by? Anybody? So if I took the derivative of this, I would be multiplying by -1/2, right? The derivative of secant of -1/2 x would be secant of -1/2 x times tangent of -1/2 x times the derivative of -1/2 x, which would be -1/2. But I don't want a -1/2 in there. So I have to divide by -1/2, which I would then write as, I would write that as times -2 secant of -1/2 x. So these come up a lot where you have, you have a function you know how to anti-differentiate, but the insides are something times x. You just divide by that something you're multiplying by x. You can also do the substitution. Like for this problem, we totally could have written it out. We totally could have said, okay, I'm going to do u equal to -x/2. du is -1/2 dx. So I will say most of the time we don't write du dx equals the derivative. We go straight to saying the differential du equals the derivative times the differential dx. It's just cutting out the step. And then dx is equal to -2 times du. So then if I rewrite this integral, it's the integral of secant of u, tangent of u, and dx is -2 times du. The antiderivative of secant of u times tangent of u is just secant of u, and then plus c, and then plugging back in u, you get -2 secant of -x/2. Which wow, yeah. Sorry, I totally made a mistake over here and wrote the tangent again. I apologize. Maybe that's why you guys were like, I don't know what he's talking about. Sorry about that. This should have just been -2 secant of -1/2. I don't know. I definitely had that right here, and then I simplified it very poorly by throwing in an extra tangent. Yeah. So people ask me questions. Someone asked, can we think about this as kind of a partial u sub? I have trouble doing it in my head. You can always write this out. So this is total. This is not just a partial u sub. It is actually literally a u substitution. I just find it to be a small, or what I call a mini u substitution, meaning I personally like to not have to write it out if I can, because here's the problem. We're going to see other integrals eventually where, in addition to having a small u substitution, there is some other stuff going on as well, which makes it just a little bit even more complicated. So oftentimes, if we can just do the small u sub without having to write it all out, it's to our benefit. That said, it is still perfectly valid and right and okay to write out the u sub. So if you want to write it out, you should write it out. If you don't want to write it, you don't write it out. But I will also say it's always a safe choice to let u equal a multiple of x. You can always do the u substitution if that's something that's popping up. Whereas other choices were like if you're letting u equal x squared or x cubed or something else, depends on kind of if you have the other thing there. But if you're letting u equal a multiple of x, like for example, if you're integrating, I don't know, let's make it easy, like cosine of 4x dx, it's always safe to let u equal a multiple of x, because if u is 4x, the derivative is just a constant. And we can always adjust for a constant multiple. Right here, you're going to get 1/4 du equal to dx. And then this is going to become the integral of dx becomes 1/4 du. And cosine of 4x becomes cosine of u. The antiderivative of cosine of u is sine of u. So we end up getting 1/4 sine of 4x. Let's see. But it really is perfectly okay to just say, oh yeah, I know the antiderivative of cosine of x is sine of x. So I know the antiderivative of cosine of 4 times x is sine of 4 times x, but then I have to divide by the 4. Okay. Let's see. There was a couple different directions I wanted to go. Someone asked me. Yeah. So I definitely want to get to the other trig antiderivatives. But before I get there, a couple people asked questions about like, what's the difference between a definite integral and an indefinite integral? Let's talk about that for a minute. So, indefinite integral has the same meaning as an antiderivative. People use these words interchangeably. In fact, people really use the word integral and antiderivative interchangeably. But they really should be saying, when someone says an antiderivative is an integral, they really mean the antiderivative is an indefinite integral. And here's an example. The indefinite integral of, I don't know, let's say 3x squared plus secant squared of x dx. When you do an indefinite integral or an antiderivative, you just antidifferentiate. You get x cubed plus tangent of x plus c. And what I want to point out is when you have an indefinite integral, your answer is always a function. Plus c. On the other hand, a definite integral, in fact, we will do this same integral, but we'll do it definite. So a definite integral we can recognize when you have limits of integration. So we could say, we could do this from, let me pick some numbers that are not super terrible here. We could do the integral from, wow, that's going to be kind of terrible either way. Let's do 0 to pi over 4 of 3x squared plus secant squared of x dx. So the process now here is to first, we still antidifferentiate, which is why this symbol is used to mean the antiderivative, because when you do a definite integral and you use the fundamental theorem of calculus, you're using the antiderivative to evaluate it. So antidifferentiate, you get x cubed plus tangent of x. We don't need the plus c here because when you do the rest of it, it just cancels out from 0 to pi over 4. And then we plug it in. We plug in the top limit first. So we get pi over 4 cubed plus tangent of pi over 4 minus 0 cubed plus tangent of 0. Pi over 4 cubed is just pi cubed over 64. And tangent of pi over 4 is just 1. 0 cubed is 0, tangent of 0 is 0. So this is equal to that. So here for a definite integral, the answer is always a number. And it represents some area between curves or above the x-axis or whatever, but it's representing some sort of area. So really, really big difference. Indefinite integral, you get a function, which is the antiderivative of whatever is inside your integral, and that's it, you're done. You get a function, slap on a plus c. For a definite integral, you're calculating an area. Here, we're calculating the net area under the curve 3x squared plus secant squared of x between 0 and pi over 4. And you do the antiderivative, you plug in your limits of integration, and then you get some numerical answer, which is how much area there is. That's it. That's the difference between an indefinite integral, aka an antiderivative, and a definite integral, aka an area under a curve. So I don't remember who asked that question, but hopefully whoever asked that question, that helps. Okay, let's go ahead and quickly talk about the last 4 trig integrals, which are the integral of tangent x, cotangent x, secant x, and cosecant x. And here's the nice thing. I know I erased the derivatives, but we still have the antiderivatives. So just like the derivative of tangent and cotangent are very similar, right? The derivative of tangent is secant squared x. The derivative of cotangent is negative cosecant squared x. So I'm just putting a co on each of them. And the same works for secant and cosecant. The derivative of secant of x is secant of x times tangent of x. The derivative of cosecant of x is negative cosecant of x times cotangent of x. So I just took everything in this equation and put cos on each of the trig functions and a negative sign. What I'm trying to say in a lot of words is there's a very similar relationship between the integral of tangent and cotangent. Integral of tangent is going to be something, integral of cotangent is going to be very similar related like their derivatives are. Integral of secant is going to be something, integral of cosecant is going to be very related. But they are a little bit complicated. They do both require a U substitution. And I don't remember, because again, I teach this class and 21 beyond this. I don't remember if we did the antiderivative of tangent last week or not, but it's worth seeing again. So we'll do them all real quick. They're not too terrible. The secant one does require a trick. Also, what I will say is you guys are going to want to memorize these, or at least memorize them for tests, because you probably, I don't know, if you're allowed a cheat sheet, then maybe not, but you're going to do these enough that you're going to need to memorize them. Or not if your teacher says you don't, but I think you should. Okay, so I want to find the antiderivative, also known as the indefinite integral of tangent of x. So the first step is to write this as the integral of sine of x over cosine of x. And then we're going to do a U substitution. Now, I should ask you guys, what should I choose for U here? Should I choose U equal to sine of x, or should I choose U equal to cosine of x? It might seem like both choices are perfectly fine. So that's a good suggestion. We can try cosine. So can anyone tell me why sine might be a bad choice? So often when I do this problem, people are like, oh, sine, because the derivative of sine is cosine, which seems nicer than the derivative of cosine being negative sine. But someone's exactly telling me, right, that sine is in the, sine is in the numerator, which is actually okay. Right, it's more that, well, I mean, it's not okay, right? We like to pick the thing that's stuck somewhere. And if I have a choice, I'm going to pick the thing that's stuck in the denominator versus the numerator. But the real issue here is that if you use sine, then your du is cosine of x times dx. And then again, I don't remember if I said this last week or not, but this integral does not have cosine of x times dx. It has a 1 over cosine of x times dx. Right? You can write this as sine of x times 1 over cosine of x times dx. That's not the same as this. So this actually is not a good choice. We let u equal to cosine on the other hand, then your du, right, is going to be negative sine of x times dx. And we're going to adjust for the negative. We're going to say that negative du is positive sine of x dx. Sorry, I'm a little raspy here. So then we're going to say this is equal to the integral of, so sine of x dx is negative du, and cosine of x is just u. And personally, I like to rewrite this so that the negative is out front, and du over u is 1 over u. All right, so then 1 over u becomes, well, I should say, the integral of 1 over u is the natural log of the absolute value of u. So it's going to be negative natural log of the absolute value of u plus c. Then we have to plug back in what u is equal to. It's going to be the negative natural log of the absolute value cosine of x plus c. And that is how most people write this. There is an alternative form of writing it. I don't know if your teacher has talked about it, but this -1 coefficient, you could rewrite this as the natural log of the absolute value of cosine of x to the -1st power. And then cosine of x to the -1st is 1 over cosine. So this is the natural log of 1 over the absolute value of cosine of x. But 1 over the absolute value of cosine is the same as the absolute value of secant. So this is equal to the natural log of the absolute value of secant of x. Sorry, I lost my plus c. And this is another valid way that people write it. I personally prefer to write it this way because it matches up more with how we write the integral of cotangent, but that's the integral of tangent of x. Let's do cotangent. It's going to be very much the same. So let me tell you this. The integral of tangent is negative natural log of the absolute value of cosine. The integral of cotangent is going to be the positive natural log of not cosine, but cosine, which is sine. Right? If you take a cofunction of a cofunction, you get back to the original function. So you're going to get natural log of sine. Let's see. In fact, you guys could probably do this one all on your own. So the integral of cotangent of x is the integral of cosine of x divided by sine of x. And now we're going to make the u substitution that u is equal to sine of x, taking the thing in the denominator. Du is equal to cosine of x dx, and look, that works out perfectly. That's du, sine of x is just u. And just like before, the integral of du over u, or if you prefer, the integral of 1 over u du, that's going to equal the natural log of the absolute value of u. Plus c. And then plug back in what u is, that's the natural log of the absolute value of sine of x. Done. Technically, there is an alternate way of writing this as well, but we do not do it that way. It's always this way. Secant and cosecant require a trick. It's actually really kind of interesting. So I got bored one day and was thinking about this integral, and I was like, I wonder how they came up with that. So I Googled, well, in fact, let's talk about what they do before I talk about how I found out stuff. That's kind of interesting. So here's the trick for integrating secant of x, which you don't have to remember the trick, you have to remember the integral. You have to multiply secant of x by secant plus tangent over secant plus tangent. And I'm going to do it slightly out of order. I'm going to do it as tangent of x plus secant of x over secant of x plus tangent of x. Same difference, just you'll see. So one day I was like, where the heck did this trick come from? Like, how do they figure out that that's what you do to figure out the integral secant? Well, it turns out the way you actually integrate secant is by doing some crazy stuff where you use partial fractions, which we will talk about, I think, in this class. But it's really kind of interesting. It actually, so the integral of secant x, you might be like, James, who cares about the integral of secant of x? Well, map makers care about the integral of secant of x. So if you look at the map that everyone has looked at, called the Mercator projection map, where they take like the globe and they like fold it out onto a map, and you see that like the parts away from the middle are much longer, right? And Greenland looks super huge, even though it really isn't as big as it looks on a map. What's interesting is basically the amount of stretching out that happens as you move further away from the equator is exactly given by like the ratio that's the integral of secant of the angle that you are from the equator. So this integral actually comes up in interesting places. Like, it's not just whoever would care about this. Lots of people actually really cared about this when they were making maps back in the day. So kind of neat. Definitely, if you're interested, you should Google it. It's kind of a neat thing. Not super important to us probably, but still neat. But then they're like, oh, but then there's another easier way of doing it. So we're going to do it this way. So I'm going to multiply the secant out, or the distribute secant through. So secant times tangent is secant x tangent x. And secant times secant is secant squared x. And the denominator is still just secant x plus tangent x. But then check it out. If we let u equal the denominator, and I'm going to erase the top part. Yeah, right here. Erase up here. Sorry, I know. This is the integral of cotangent of x. But if we let u equal the denominator, u is secant x plus tangent x, then your derivative, the derivative of secant is secant x times tangent x. The derivative of tangent x is secant squared x. But look, that's exactly the numerator we have. So this is exactly du over u, which is the natural log of the absolute value of u plus c, which is equal to the natural log of the absolute value of secant x plus tangent x. Kind of bananas. And then we could do the other one, but I don't think we really need to. I will just tell you. In fact, let me write them all down. So here are the integrals of the 6 trigonometric functions. The integral of sine of x is negative cosine of x plus c. The integral of cosine of x dx is sine of x plus c. The integral of tangent of x dx, we just found out was negative natural log of the absolute value of cosine of x. Let's see. The integral of secant of x dx is equal to the natural log of the absolute value of secant of x plus tangent of x. Let's see. The integral of cotangent of x dx is positive, not negative, natural log of the absolute value of sine of x plus c. And the integral of cosecant of x, I believe the way your teacher has written it is as the, I don't remember actually what I saw. I believe it was the natural log of the absolute value of cosecant of x minus cotangent of x. Let's see. Kind of crazy. Very similar though, right? Integral of secant is natural log of secant plus tangent. Integral of cosecant is the natural log of cosecant minus cotangent. So I took all the trig functions here and I just put cos on each of them and then change the sign. If you've ever seen this before, you might have heard that the integral of cosecant of x dx is equal to the negative natural log of the absolute value of cosecant of x plus cotangent of x. This formula are actually equal to each other. If you ever wanted to check, you could show that this and this are actually equal to each other by bringing this -1 up as the power and then showing that natural log of this to the -1 is the same as natural log of this. That's not super important, but I do want to just cover all my bases and make sure that if, in case you've ever seen it this way, yes, this is also valid. I prefer this personally because I like the idea of putting like the integral of the co-function is the negative of the integral of the original function, but change the functions to their co-functions. All right, I think that covers not all the trig stuff we'll ever see, but that definitely covers all the trig examples. So, let me know if there's any questions about that before we start hitting the U substitution super hard. Okay, we can always come back to this, right? If you have questions about trig integrals, then ask away whenever you want. But I do think, right, when you see like the integral, so for example, if someone said, hey, what is the integral of, I don't know, cotangent of 3x dx? Could do a U substitution, or we could do the mini U sub inside our head and be like, okay, I know I'm going to end up dividing by 3. Why am I going to divide by 3? Because if we did the U substitution, u equals 3x, du equals 3dx, and 1/3 du equals dx. So that if I did the u sub, dx gets replaced by 1/3 du. Oh, I'm going to end up dividing by 3 or multiplying by 1/3. That's why it happens that way. Because when your u is equal to a multiple of x, when you isolate dx, you end up dividing by that multiple of x. Always, always, always. But I don't want to do that. I just want to be like, I know the integral of cotangent of 3x. Well, I know the integral of cotangent of x is natural log of sine of x. So the antiderivative of cotangent of 3x is the natural log of the absolute value of sine of 3x. Then I have to divide by 3. Or you can write it as 1/3 the natural log of the absolute value of sine of 3x. We don't care. I'm cycling through my pens here so I don't use one up all right away. I got some fresh ink from Sarah this morning. Okay. So kind of back on the u substitution train. We're going to do a lot of problems here. When you're thinking, and again, right, eventually, once we learn other methods of integration, the question we're going to have to ask ourselves is, what method of integration should I even try? Does it look like I should try a u sub, or does it look like I should try something else? Usually, u sub is what I think of first, right? Like, can I do a u sub? I would love to do a u sub because it's usually like the easiest thing to do. So I usually ask myself, does this meet the criteria for u sub? Meaning, does something look like it's stuck somewhere? And the something that's stuck is its derivative also showing up. So here's an example. I don't remember who, sure. So someone asked me, I think this is what they asked me, 1/x times the natural log of x. It was to the 5th. I'm going to change it to the 6th, just so I'm not exactly doing your homework problems, but very, very similar. So here's what I see. I mean, I see a few things stuck. I see the x stuck here, I see the natural log of x stuck there. But I'm going to try natural log of x for 2 reasons. One, yes, the natural log of x is indeed stuck right there. But probably more importantly, its derivative of the natural log of x is 1/x. And I have a 1/x. Right? I don't have to, but I could rewrite this as 1/x times 1 over the natural log of x to the 6th times dx. And then I can see, oh yeah, my du is equal to 1/x dx. And look, we exactly have that. This part right here, that's equal to du. So then when I write my integral, it's going to be the integral of, well, that part there is just du. And then this remaining part here is 1/u to the 6th. Now, of course, when you have a 1 over something to a power, you should rewrite it as the integral of that thing to the negative of that power. Then we're going to use the anti-power rule. We're going to get u to the, let's see, -6 plus 1 divided by -6 plus 1 plus c. -6 plus 1 is -5. So that's going to give me u to the -5th divided by -5 plus c. And then finally, we have to go back. And if it's so I will also point out, if it's an indefinite integral, whether or not you're using u sub or whatever, you always should end up with the same variables you started with. So if I started my integral as an integral of x, my answer at the end should be a function of x. So I need to plug back in that u is equal to natural log of x. That's going to be the natural log of x to the -5th over -5 plus c. Or if you want to make it maybe look a little bit nicer, I would probably write it as -1/5 times the natural log of x to the +5th. Yeah. And so if it was natural log of x to the 6th instead of x, or natural log of x to the 5th instead of 6th, I imagine your answer would be essentially the same, except it'd be -1/4 natural log of x to the 4th probably would be your answer. I should ask you guys. Actually, let me look at your homework before I just start asking away. Have there been definite intervals with u substitution? I don't see any there. I don't see any definite integrals with u substitution on any of your homework assignments yet. Okay, then we'll not do that just yet, unless you guys want me to. I'm happy to do some definite integrals with u sub if you would like, but since I don't see any on any of your homework assignments, we probably don't need to yet. We should probably just do all the u subs in the world. So again, I've written down all the questions you guys asked in the reflection, taking those as inspiration. I'm probably gonna switch them up a bit. Oh, you know what? Here's one we should definitely look at though. And this one comes up quite often. And I feel like now I'm looking back to your homework. Did I see any problems like this before I get super started on it? Yeah, I see a couple. Okay, cool. This is actually on the homework assignment. So for Lee, I know your homework assignment 3 is due today. Homework assignment 4 starts next week. But there's a couple problems in homework assignment 4 that I would love to kind of riff on. So we know the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. Now, what about the integral of, say, 1 over x plus 3? Well, we could do a u sub. We could let u be what's stuck in the denominator. Du is equal to, well, the derivative of x is just 1, so it's 1 times dx. That's kind of the easiest u sub ever when u is just x plus a number. Then you're going to let this be 1 over u, and du is dx, so dx is replaced by du. That's going to be the natural log of the absolute value of u plus c, which is the natural log of the absolute value of x plus 3. So if you have 1 over x plus a number, you get still the natural log of just that thing. Of the natural log of the absolute value of x plus 3. What if the denominator was a little bit less nice? What if it was, say, like the integral of 1 over 2x plus 3? Are there any guesses as to what we're going to get? Well, I'm thinking let's do u substitution. U is going to be the denominator. My du, the derivative of 2x plus 3 is just 2 times dx. And then I don't have a 2 dx, I just have a dx, I'm going to divide both sides by 2. So du divided by 2 equals dx. So now I'm going to rewrite this. This is the integral of, so dx is du over 2. You know I would rather put that 1/2 out in front. And then 1 over 2x plus 3 is just 1 over u. The integral of 1 over u is still the natural log of the absolute value of u. So you get 1/2 the natural log of the absolute value of u plus c, which is 1/2 the natural log of the absolute value of 2x plus 3 plus c. And here's what happens more generally. If you're ever integrating 1 over some linear function of x, like 1 over mx plus b, your integral is always going to be 1 over m times the natural log of the absolute value of mx plus b plus c. And that's true because, well, if you take the derivative of natural log of some stuff, you get 1 over the stuff times the derivative of the stuff, and the derivative of mx plus b is just m. And the m cancels the 1 over m. So the derivative of the natural log of this is just 1 over mx plus b, which is exactly that. Be aware. This is a very common mistake I've seen a ton of people make. The integral of 1 over x squared plus 1 is not equal to the natural log of the absolute value of x squared plus 1. Why not? Because the derivative of this is not equal to that. Let me erase here. I think I need a little bit more room. Yeah. So if you take the derivative of that, the derivative of the natural log of x squared plus 1, I'm going to drop the absolute values because x squared plus 1 is always greater than or equal to 1. That's 1 over your stuff times the derivative of your stuff. Oh, that's 2x over x squared plus 1. That's definitely not 1 over x squared plus 1. Here's the other thing you cannot do. You can't say, okay, well, James, you said like before we divide by the derivative. So can we do that here? Can we say that the integral of 1 over x squared plus 1 is equal to the natural log of x squared plus 1 divided by 2x? And that's a definite no. Right? You can only divide by the derivative of the thing if the derivative of the thing is a constant. Here, if you try to take the derivative of this, you'd have to use the quotient rule, right? The derivative of the natural log of x squared plus 1 over 2x is gross. It's the bottom times the derivative of the top, which is 1 over x squared plus 1 times 2x, minus the top times the derivative of the bottom, which is natural log of x squared plus 1 times 2, over the right. That is definitely not 1 over x squared plus 1. So just want to be extra explicit. You can only do this dividing by the derivative of the thing kind of trick if the thing that you're taking the derivative of is a multiple of x or a multiple of x plus a constant. Those are the only things that works for. Other more complicated things doesn't work. All right. So more u subs. More u subs. Let's see what's on my list here. Okay, I got lots of problems here. I got 99 problems, and u subs are not one of them. I mean, they're all of them, but you know what I mean. So let's look at this one. Let's look at the integral of, sure, 7x cubed over the square root of 3x to the 4th plus 1 dx. Some of the numbers in this problem have been changed to protect the innocent. All right, so there's clearly a candidate for u here. It's the thing stuck inside the square root that's in the denominator. And again, for both reasons, right? It's stuck, but more importantly, if you let u equal 3x to the 4th plus 1, the derivative is essentially, and when I say essentially, I mean they were just off by a constant multiple. The derivative is 4x cubed, and I have an x cubed. Great, I can make it work. Like Tim Gunn says, make it work. Tim Gunn says that? Make it work? I don't know. Maybe that's not what Tim Gunn says. Anyway, I think that's what he says. Right. Project Runway, for those of you that don't know, Tim Gunn, make it work. I think that's what he said. Anyway, du equals 4x cubed times dx. I don't have a 4. If that was an 8, I might just say like 2 du is 8x cubed dx. But instead, since this doesn't really work nicely, I don't want to go to 7/4 du is 7/4. I mean, you could, but I would rather just say 1/4 du equals x cubed dx. So that I can grab this and say that's my 1/4 du. So I'm going to do two things. I'm going to pull out the 7. X cubed du is going to be, sorry, x cubed dx is going to be 1/4 du. And in the denominator, I'm going to have the square root of u. And did I make them? Did I? Yeah. Why? That's an excellent question, Joanne. Wow. Oh man. Yeah, I feel kind of terrible about that. Yeah. Good point. The derivative of x to the 4th is 4x cubed. The derivative of 3x to the 4th is 12x cubed. Sorry about that. This actually, although not the mistake, I think I have seen a fair number of people when differentiating something make the mistake with the power rule of like saying, I've seen a number of people say like the derivative of 3x to the 4th is 12x. They've kind of forgotten that the power has to be 1 less, not just whatever. So do make sure that when you use the power rule, I know it's a different mistake than what I made, but when you use the power rule, make sure that your power just becomes 1 less what it was. But yeah, totally right. I totally missed the coefficient of 3 there. So 12x cubed, 12x cubed, so this would be 1/12 du equal to x cubed dx. Please do keep me honest. I am sad to admit, I feel like I make a few more mistakes these days than I used to. So be on the lookout. I will make a mistake occasionally. It's usually not intentional. All right, so then let's rewrite this. Let's bring up the 1/12. And let's rewrite 1 over the square root of u as u to the negative 1/2. Then we will integrate that. We'll get u to the positive 1/2 divided by positive 1/2. Dividing by 1/2 is the same as multiplying by 2. So this is going to be 7/12 times 2 times u, which is 3x to the 4th plus 1 to the 1/2. Let's see. Wow. That's really sloppy notation there. After you integrate, you shouldn't be writing du anymore. There should be a plus c. Not my best work. So anyway, 7/12 times 2 is going to be 7/6. And I would probably rewrite this as the square root of 3x to the 4th plus 1. Although it's not absolutely necessary to do that. So when we're looking at something that we think is a u substitution, we are always on the lookout for, is the derivative of the thing I want to pick for u also in my integral? Let's look at another one. Let's look at something like this. Let's see, what time is it? Oh, we got time. We got lots of time. Sure. Here's one. Let's say we've got the integral of, let's say 8x plus 12 over x squared plus 3x plus 7 to the 4th. So, as usual, our candidate for u is stuck in the denominator. It's stuck inside something being raised to a power. You could also ask the question, right? You could say, what's the integral of, I don't know, let's say, just to make it a little bit more interesting. We could also look at this one, 8x plus 12 times secant squared of x squared plus 3x plus 7. Both of these problems have the same u choice. And either one of these, we're going to try letting u equal x squared plus 3x plus 7. Because they're both stuck. And hopefully, both of them have their derivative also in the integral. I mean, they have the same pieces, so if one of them does, the other should. So our du here is going to be 2x plus 3 dx. And it looks like I have that. I mean, I don't exactly have it, but I could either, so there's a couple ways to do this. I probably would, I don't know, actually either seems fine. You could either multiply this by 4 on both sides and say 4 du equals 4 times 2x plus 3 dx, which is exactly 8x plus 12 dx. Or you could factor out the 4 from the integral. Either way would be fine. So in this particular integral, we're going to say, okay, well, that's equal to 4 du. So I'm going to have the integral now of 4 du over u to the 4th. I'm going to rewrite that as the integral of 4 u to the negative 4th du. And then I'm going to use my anti-power rule. It's going to be 4 u to the negative 3rd over negative 3 plus c. And then that's going to equal negative 4/3 times u to the negative 3rd. And you can leave it like this, or you can bring that, you can write it as negative 4 over 3 times x squared plus 3x plus 7 to the positive 3rd. Same idea here, right? You're making the literally exact same choice. So now here, that's my 4 du. So this integral becomes the integral of 4 times du times secant squared of u. We know how to integrate secant squared. It's tangent. This is going to be 4 times tangent of u plus c, which is then 4 times tangent of u, which is x squared plus 3x plus 7. Let's see. So I know I'm sounding like a broken record here, but when you're picking u, you're trying to pick the u that's stuck, and so that the choice for u, its derivative, also is in your integral, or really a multiple of your derivative, right? We can always fix or adjust for being off by a constant multiple. Let's look at a couple more, and then we'll do a few other things. Let's see what I've got here. Sure, let's look at that one and that one. So I was asked these 2 questions. Let's do this one first. Do the integral of 3 over the square root of 2x plus 1. Well, let's make it a cube root. Let's spice it up a little. Okay. What's a good, so I would like at least 3 people to type in the chat, either privately or to everyone. What should I be choosing for you here? What is the choice for you? I would love to see some responses. 1. Another one. There we go. 3. Awesome. Thank you. Yes, it's the thing that's stuck. Is it derivative? Is its derivative also there? Yeah, right. Because if u equals 2x plus 1, its derivative is just 2, which is just a constant, and we can always adjust for any constant multiple. So if your derivative is just a constant, it's always like, that's a safe choice. So if you're picking u equal to some mx plus b, some linear function of x, it's always a safe choice. It might not always be the right choice. It often will be, but it's definitely always a safe choice. So then 1/2 du is equal to 2 dx. And then, 2 dx, come on. I divided by 2. That 2 is no longer there. 1/2 du equals dx. So this is going to be, I haven't said this much today, but I'm going to say it now. Whenever you're dealing with a u substitution and changing all your x's to u's, you want to make sure to take care of dx changing to whatever times du first. So that's why I'm always writing, okay, dx is 1/2 du. I always want to do that part first. And then the rest, let's see, I'm going to do 3 over the cube root of u. And then I'm going to rewrite that as, let's bring out the 3. Let's say that's 3/2 integral of u to the negative 1/3. And to differentiate, when you add 1 to negative 1/3, you get u to the negative 1/3 plus 1 is positive 2/3 divided by 2/3 plus c. Dividing by 2/3 is the same as multiplying by the reciprocal. So I thought this was going to cancel out when I set it up, but I got it backwards. It's 3/2 times 3/2 times u, which is 2x plus 1, to the 2/3. So this is 9/4 times 2x plus 1 to the 2/3. Let's see. Let me think for a second here. Yeah. Sorry, the problem I want to do is I'm going to try and make it right. Sorry, the brain is like trying to make sure it comes up. The integral of, not really there. Sorry, brain. Trying to give a good example for a thing, but it's not really what I want. Oh, I got it. How about this? How about the integral of, I feel like we might have done this one before. I'll change it up. Mechanics. Let me be extra careful here. That's not a good choice. Yeah, fine, we'll do this one. Let's do the integral of secant of the square root of x tangent of the square root of x divided by the square root of x. Any guesses as to what our u should be? It's really gonna make it, yeah, somebody type of thing. I know you guys know what it is. You can even say words. Yes, thank you. X to the 1/2, aka the square root of x. So if I let u equal the square root of x, which is x to the 1/2, my du is 1/2 x to the minus 1/2, or du is 1/2 root x dx. Now here's what I want to point out. If you kind of move through this too quickly, it's really easy to make the mistake of not catching what du needs to be. If I was trying to be like, oh, all my square root of x's become u's, I would be wrong. This is not going to work out if I say this is secant of u tangent of u over u dx. Oh, I still have a dx and dx. So here's what we should be doing. We should be being like, okay. In fact, there's actually more than one way of doing u substitutions. My personal preference is to always try and make this right-hand side look like what I have in the integral. So I multiply both sides by 2. We can say that 2 du is 1/root x times dx. And I have a dx divided by root x. So that dx divided by root x, that is equal to 2 times du. So if I was actually going to rewrite my integral, it'd be the integral of, well, dx over root x is 2 du. I've taken care of all the circled stuff. I no longer have to worry about it. So then the rest of the integral is secant of u tangent of u. We know how to integrate that. That's secant of u plus c, and then that's 2 secant of the square root of x plus c. I will mention it's not my favorite way of doing it, but some people like to be like, well, James, you could just take dx and say, you can take dx right here and say that dx is equal to, it feels dumb. Dx is equal to 2 square root of x times du. And then people are like, then they replace the dx first. And they say, instead, I'm going to write this as the integral of secant of the square root of x, tangent of the square root of x, over the square root of x, times 2 square root of x du. I know I wrote a dx over here. That was a mistake. And then the square root of x's cancel, and then the other things become u's. I don't like doing it that way, but it's not wrong. If you like doing it that way, perfectly fine. I just don't prefer to do it that way. I think that's kind of weird. Perfectly fine. Let's see. And it would still work out the same, which is what's important. There was one more question somebody asked me before I get to, I can fit it all in. So let's look at this question. Here's the last u substitution I have for the moment, and we have a couple non-u sub integrals. I feel like I'm reading this one wrong. Yeah, sorry, my handwriting here, I kind of failed to write that down correctly. Now I'm really curious. Sorry, 1 minute. I'm gonna look real quick just to see. I think it's right there. Okay. So somebody wrote me this one, and I actually. Oh no, that should be fine. I'm just, yeah, sure. And I'm going to change it up just a tiny, tiny bit. We get x squared plus 4 over the square root of x cubed plus, sorry, the cube root of x cubed plus 12x. Someone asked me a problem very similar to this. It was actually x squared plus 3 over x, the cube root of x cubed plus 9x. But again, I hope to feel like at this point, the choice for you, I think, should be obvious to everybody. I hope. Right? We're always thinking it's probably the thing that's stuck. It's probably the thing, look, this is x cubed plus 12x. The derivative is going to be something x squared plus a constant. I've got something x squared plus a constant. That's looking like a pretty good choice. So if u is x cubed plus 12x, our du is 3x squared plus 12 times dx. And if I factor out the 3, I can divide both sides by 3 and say 1/3 du is equal to x squared plus 4. So we're in a good spot. As always, I'm going to deal with making sure the dx transforms into the du before anything else. So that right there is my 1/3 du. So it's going to equal 1/3 du divided by the cube root of u. And then I would rewrite this. I would always pull out the constant multiple in front of the integral. I would write this as u to the negative 1/3 du. And to differentiate, 1/3 u to the negative 1/3 plus 1 is positive 2/3 divided by positive 2/3 plus c. Flip and multiply, you get 1/3 times 3/2 times u, which is x cubed plus 12x, to the 2/3 power plus c, and then 1/3 times 3/2 is just 1/2. So 1/2 x cubed plus 12x to the 2/3 power plus c. So I know I've said it like a million times. I'm going to say it another time. When you're looking to choose a u, choose a thing that's stuck somewhere. If you have a root, a cube root, any kind of root, usually the thing inside the root. You have a trig function, the stuff inside the trig function. If you have e to the something and the something's complicated, the something's a good choice. Right? It's always the thing that's inside of another function or in the denominator, which is still inside another function, right? Because if you're in the denominator, you really, like if I had the integral of say 2x over 4x squared plus 1, being in the denominator means you're really in the function being raised to the negative first power. You're still stuck. So if something is stuck somewhere, that is almost always, at least where you want to start. Maybe it doesn't work out, but that's always the best first kind of guess as to what you should choose for you. Okay, a couple problems that might look like U subs, but probably aren't. So I have this problem, the integral of 4 secant of y times tangent of y minus 6 secant squared of y dy. It's just using a different variable. And then the other one we have is, I'm going to change this one slightly, the integral of e to the 6x plus 5 plus 6 e to the x plus 6 all over e to the x. So this first one, these are actually integrals that we should recognize. Secant y times tangent y is the derivative of secant of y. So you can break this up if you want to, right? So here are the steps that we would never really usually write, but we could. You could totally, let me write the answer first and let me show the steps after. So I'd be like, I know the integral of secant y tangent y is secant of y, and to be multiplied by 4. And I know the integral of secant squared of y is tangent of y, and to be multiplied by negative 6. But the intermediate step that we don't ever really show is you could break this up into two integrals and pull out the constants. You could say this is 4 times the integral of secant of y times tangent of y dy minus 6 times the integral of secant squared of y. And then, oh yeah, this part here, that's equal to that part there. And this part here, that's equal to that part there. But usually we just skip over this stuff. Be like, yeah, I know the integral of that is secant of y, it's getting multiplied by 4. I know the integral of that is tangent of y, it's getting multiplied by -6. Other problem. You might guess this was a u sub. I wouldn't fault you for guessing it's a u sub, right? Because it seems like, well, I got an e to the x stuck. I can try letting u equal e to the x. And then du is e to the x dx. But I don't really have an e to the x times dx I can deal with here. And it's not what we want to do. What we actually want to do, and again, this comes from some experience. If you see a fractional thing, and the denominator has one term, meaning it's not e to the x plus 1 or the square root of e to the x plus 1, right? If it's just something not added or subtracted to anything else, right? In a similar way, right? The same thing I'm about to say for this would be true if you had something like x to the 4th plus x cubed minus 2 square roots of x all over x squared. If you have a fractional thing and the denominator has a single term, you can divide each thing in the numerator by that single term in the denominator. So I would rewrite this as e to the 6x over e to the x plus 6e to the x over e to the x plus 6 divided by e to the x. And then simplify. This is the integral of e to the 6x divided by e to the x. We subtract the powers. And 6x minus 1x is 5x. So that's e to the 5x. E to the x divided by e to the x is just 1, so I get 6 times 1. And 6 divided by e to the x is 6e to the negative x dx. And here is an excellent opportunity to use our mini u substitution powers instead of doing a u sub for this one and for this one. Right? So if you're going to actually do the u subs, you'd have to break it up into 3 integrals. And you'd be like, okay, for this one, I'm going to let u equal 5x, du is 5 dx, 1/5 du is equal to dx. So we're going to divide by 5. So this is going to be e to the 5x divided by 5. Same deal for this over here. We'd have to let u equal negative x, negative du equals dx, and then we would change the sign essentially. So the integral of 6 is 6x. And the integral of 6e to the negative x is 6e to the negative x divided by negative 1, which we usually just write as minus 6e to the negative x. So this would be e to the 5x over 5 plus 6x minus 6e to the negative x, or 6 over e to the x if you prefer writing it that way. Either way. Okay. And then let me spend the last few minutes here talking about this radioactive decay problem. So this problem says we have some radioactive material, and we know that after 2 years, 90% remains. How much or how long is the half-life? And the challenging part about the problem is that they didn't tell you how much you started with. So here's the thing. You can make any choice you want. You can start with however much you want. I typically, when I'm doing something like this, when I have time and the amount, if I'm dealing with percentages, I like to say I'm going to start with 100. At times 0, I have 100 grams or pounds or kilograms. I don't really care what the units are. You can also say you have 100%. You also say you have C, right? Those are all valid choices, but it's easiest to use the number. And then I know that 2 years later, I have 90% of what I started with. Oh, that's 90 grams. It would also be perfectly valid to use 100%, 90%, or it would also be perfectly valid to use starting with some constant C and then 2 years later have 0.9 times C. All those will work just fine. But the real honest truth here is that you kind of have to say, I know I'm starting with some whole amount, and then 2 years later, I have 90% of that whole amount. So then, here's what I know. I know that when I'm when I'm trying to find the model for exponential growth or decay, I need 2 data points. I have 2 data points. I'm good to go. I should be able to solve the system. So here's what I've got. My model is y equals c e to the kt. I decided that at time equals 0, I have 100. So I know I'm going to have y equal to 100 e to the kt. And I'm going to plug in this other piece of information that when time equals 2 years later, the amount y is going to be 90 grams. So 90, the amount equals 100 e to the k times 2. Solve for k. Divide both sides by 100. 90 divided by 100 is going to be 0.9. And I want to point out that no matter if I had picked 190 or 100% and 90% or c and 0.9 times c, after I do this division, I'm always going to end up with a 0.9 over here. No ifs, ands, or buts about it. That's going to equal e to the 2k. Take the natural log of both sides. Natural log of 0.9 equals the natural log of e to the 2k, which is just 2k. So k equals 1/2 the natural log of 0.9. So now we have found the model. The model for exponential decay is y equal to 100 e to the 1/2 natural log of 0.9 times t. But then we're asked, what's the half-life? So how much time until there's half of what we started with? Great, so I'm just going to set y equal to 50 and then solve for t. I do recommend when you have these kind of exponential growth or decay problems, writing this table, writing the time and the amount, and writing down the things you know for each of them, and then kind of filling in what you don't know. I feel like that really helps me clarify what I'm looking for. So I'm going to set y equal to 50, half of what I'm starting with. So then 50 equals 100 e to the 1/2 natural log of 0.9 t. Divide both sides by 100. 50 divided by 100 is 1/2 equals e to the 1/2 natural log of 0.9 t. Take the natural log of both sides. 50 over 100, that's the natural log of 1/2. The natural log of e to the stuff is just the stuff. So this is going to be 1/2 natural log of 0.9 t. Solving for t, multiply both sides by 2. Divide both sides by the natural log of 0.9. That's how you find the half-life. All right, it's 10:20. Stop talking. Thursday, there was one other question. Let me do one more real quick. Sorry, I'm not sure this, but this next one was really quick. I do feel like it's worthwhile. Someone asked me this one, it'll only take a second. The problem was this. It was f prime of x equals 2x minus 2, and f of 1 equals 2. Find f of x. So anti-differentiate this. The antiderivative is x squared minus 2x plus c. And then to find the c value, plug in the 1. So f of 1 equals 1 minus 2 plus c. That's supposed to equal 2. So solving for c, add 2, 4, subtract 1, 3. C has to equal 3. So your final answer is x squared minus 2x plus c. Let's call it an initial condition problem, where in addition to finding the antiderivative, they give you some initial value so that you can find the constant c as well.